Okay, this is the first video for magnetism in AP Physics C. We covered magnetism some in B last year, but we're going to cover it in much more depth this year. The first thing, though, is we need to get this idea of the magnetic field. We're going to learn what the magnetic field is and what it does. That's chapter 29. And then in chapter 30, we'll learn how the magnetic field is created. But before, let's review the definition of electric field. Now you might remember electric field is defined to be the force per unit charge on a test charge. So the idea is you have a field everywhere in space. If you put a test charge Q at a particular location in that field, it will experience a force. That force divided by the charge Q is your electric field. And in the electric field, the force and the field point in the same direction. The magnetic field is similar. It's a field, it's a vector, has a particular direction at every point in space, and that field can exert forces on charged particles. However, there are some major differences. First off, in order for a charge to experience a magnetic field, it has to be moving. In other words, a stationary charge sitting in a magnetic field, will experience no force. The faster it's moving, the stronger the force will be. Also, the electric field is always in the same direction as the electric force. That is not the case with the magnetic field. Now, the magnitude of the force, the magnetic force, is given by QV cross B. So the idea is if you've got a magnetic field pointing upward, and you have a particle with a velocity v that makes an angle theta with the field, the magnitude of the force is going to be QVB sine theta. Memorize both of those. Now the other thing is that the direction of the force will be perpendicular to both the magnetic field and also to the particle's velocity. And if you look at this diagram here, there are only two vectors that are perpendicular to both V and B. Those point into the page and out of the page. Now to determine which one we use the right-hand rule. I discussed that on the next slide, but the important part is it's like the electric field in that there's a field at every point in space, and that exerts a force on charged particles, but the way you calculate the force is very different. So to determine the direction of the force, you start by pointing your index finger in the direction of V. I'll go ahead and replicate the diagram we had. And then your remaining fingers in the direction of the magnetic field. The result is your thumb will end up pointing in the direction of the force. So with this diagram, index finger points in the direction of the velocity, kind of up and to the left. Other three fingers point upward, and that means that the force is into the page. The result of this is that magnetic fields are inherently three-dimensional phenomena. And because we'll be drawing three-dimensional diagrams, here's some conventions. A vector that's into the page will represent by a circle around an X. And out of the page will represent by a circle with a dot in it. So in this case, the force points into the page. Another thing to notice before we move on is that if the particle's velocity moves in the same direction as the field, so theta equals 0, there's no magnetic force, which is kind of interesting. Now the last thing is, if you've got a negative charge, the force is going to point in the opposite direction. So if the particle above were an electron, the force would come out of the page, because the right-hand rule says into the page. Now here's an example. This is problem 3. You've got a proton traveling at 23 degrees with respect to a magnetic field, magnitude 2.6 millitesla. That is the SI unit for magnetic field, is the Tesla. 1 Tesla is quite a large field. And this proton experiences a magnetic force of 6.5 times 10 to the negative 17 newtons. We want to find the proton's speed. So for the equation we use for the magnitude of the force, F equals QVB sine theta. And we're looking for V, so that's F over QB sine theta. And we're told that the force is 6.5 times 10 to the negative 17 newtons. Now the charge on the proton is the same as the charge on the electron, just positive, so 1.6 times 10 to the negative 19 coulombs. Magnetic field is 0.0026 Tesla times the sine of 23 degrees. And you put all this in your calculator, you find that the velocity of the proton is 4 times 10 to the 5th meters per second. Now, should you forget, say, what the charge of the proton is, you can look it up in one of the appendices of your textbook. I think it's Appendix B. Next thing we'll do is find the proton's kinetic energy. This isn't strictly a magnetic field question, but a lot of times when we talk about elementary particles like this, we're more interested in their kinetic energy than their speed. And we're going to use it in units of electron volts, which I'll explain in a second. Now K is 1/2 mv squared. You can look up the mass of a proton in your textbook, but it's 1.67 times 10 to the negative 27 kilograms. And V is what we just found in the first part of the question. And that works out to be 1.34 times 10 to the negative 16 joules. Now the electron volt is a unit of energy, and 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. It's the amount of energy that an electron would have if you accelerate it through a potential difference of 1 volt. So we have 1.34 times 10 to the negative 16 joules divided by 1.6 times 10 to the negative 19 joules per electron volt, and that works out to be 835 electron volts. So you could get a proton up to this speed by accelerating it through an 835 volt potential difference. Incidentally, that's not particularly high energies for a proton. Tomorrow I'm going to check questions 1 and 2 from chapter 29, and then next time we're going to look at the motion of charged particles in magnetic fields.